Just for fun, let's do some review. I want you to find the median and I should write that. And the standard deviation. Now I left off the mode. Why would I leave the mode off? There isn't one. There's a small set of numbers like this, the mode is kind of meaningless. Mode is only useful for numerical data if it's a large set of numbers. Otherwise, the mode is generally more useful for categorical data. I also left off the range because, well, I'm just not that nice to let you answer. So answer those three quick. We'll do them in a. How do we find the mean? Okay, so n equals 5. Why does n equal 5? There's 5 numbers in that list. So we're going to do 21 plus 28 is 49, plus 32 is 81. What's that? 150 it adds up to? Thank you. It's 150 divided by 5 gives us a mean of 30. Our median, how do we find a median? First step is always to put them in order, right? They're already in order from small to large, so we're good. Second step is to find that position, so it's n times 0.5, or 5 times 0.5, or 1/2. We get 2.5. Since n was odd, we round up. So it's the third number in the list. 1, 2, 3, it is 32. Relatively close to our mean. What does that tell us about the skew here, by the way? If the mean is smaller than the median, probably skewed left. Median would be somewhere in here, mean somewhere over here. If the mean is to the left of the median, it's skewed left. The mean is to the right of the median, it's skewed right. Standard deviation requires a touch more work. What's step 1 of the standard deviation? Okay, so the mean equals 30. That was easy enough. Step 2. Subtract the mean from each. So we got 21, 28, 32, 33, 36. And what are we going to do with each of those? Subtract the mean of 30. So 21 minus 30 is -9. 28 minus 30 is -2. 32 minus 30 is a positive 2. 33 minus 30 is positive 3. 36 minus 30 is 6. What are those numbers called? They're referred to as the deviations. What should they add up to? 0. So that's one way to double check yourselves here. Step 3. One more step. Get square. Square the deviation. So -9 squared is positive 81. -2 squared is positive 4. Remember, anything squared should be positive. 2 squared is 4. 3 squared is 9. And 6 squared is 36. And then step 4 is find the sum. So we have what? 134. Step 5 is where it gets a touch tricky. You got it. 5 by n minus 1. So since n is 5, n minus 1 would be 4. 33.5. Of course, that number is referred to as the variance. To get our standard deviation, we have to do one more step. Square root. Square root of 33.5 gives us 5 point. We'll go 5.79. What do you think? So none of the steps are terribly difficult. Remembering to do all of them is the hard part. Let's talk about measures of position. Talked about measures of center and spread. That describes the whole distribution. Measures of position describe the location of one number within the distribution. The main one we're going to talk about is percentiles. You've probably heard this before if you've had kids or done any sort of standardized testing. Have you told, well, your kid's height is in the 73rd percentile, or your test score puts you in the 81st percentile? What does that mean? Where the percentile is the percent of the whole population. Now remember, the whole population doesn't necessarily mean all people in the whole world or all items in the whole world. It's all things that pertain to that topic. Like if you took a test, the population would be all people who have ever taken that test. So the percent of the whole population that is smaller. So let's say you take a test and you're told, oh, you placed in the 62nd percentile. Did you do fairly well? Well, that's saying 62% of people did worse than you. Now, a lot of people think, well, that's not very well, but think about it. What would average be? 50% would be average. So if you're in the 62nd percentile, you're above average. Percentiles are not subject to inflation. That's something in the educational system has become a huge issue. It's actually something that's a hot topic at a lot of conferences right now is grade inflation. How 20 years ago, the most common grade given in a college class was a C, or was the borderline between a B and a C. Now, the most common grade given in a college class is an A. So they're talking about grade inflation. Well, part of the problem is the expectation. The expectation is I'm going to go into a class every day. Percentiles are not subject to that. Just because the expectation is that everybody is going to be in the 80th and 90th percentile, it can't be possible. Half of the people have to be in the lower 50%, half have to be in the upper 50%. That's just the way it works. If everybody starts doing better, guess what happens? Well, the whole scale slides up, and you're still half of you in the lower half and half of you in the upper half. So let's take a look at how those percentiles work. Now, when dealing with percentiles, the first thing you must do, obviously we're dealing with numbers. Just like with the median, must put the items in order from smallest to largest. To save us time here, all the number sets I'm going to give, I'm going to put them in order to begin with. So let's give you a set of numbers here. 13, 21, 24, 26, 26, 7, 30, 34, 36, 40, 45, 51, and 59. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'm going to go one more. 68. Just because it's a whole lot nicer when you have that number. First of all, for this data set, little review, what's n equal? 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. N equals 14. Now, there is a good reason why I just numbered all of them. It just wasn't because I was moving my lips when I counted. Having them numbered like that's going to be helpful for us in the next step. Let's say I'm asked to find the 30th percentile. Just like with the median, my first step is to put them in order. Already done that. And also, just like with the median, my second step is to find the position. So my position is going to be n times the percentile. So in this case, that's going to be 14 times 0.30. Where'd 0.30 come from? 30th percentile. Now we get 4.2 here. So now we're going to go back and we're going to expand on the rule that we put out there for median. For median, we talked about if n is even or if n is odd. Well, the reason it's different is because when n is odd, the median is always a decimal. The location of the median was a decimal, wasn't it? Whenever it's a decimal, now in the median's case, it's always going to be 0.5. It's always going to be that decimal. But whenever there is a decimal for a position, we round up. Even though that's 4.2, we still round up to the fifth position. What number's in the fifth position? 26. So our 30th percentile here is 26. How about if I ask you to find the 70th percentile? Tell me what to do. 14 times 0.7. 9.8, which is telling us 10th one. Right? Always round up. Even if 9.1 or 9.9, it rounds up to 10. Ask you to find the 50th percentile. 14 times 0.5 is 7, right? That is not a decimal, is it? That's a whole number. Just like with the median, when we got a whole number, it is between that position and the next. So between the 7th and the 8th, we have to add those together and divide by 2. And yes, it is 32. Side note, we took n times 0.5. When else have we seen that? Yeah, the 50th percentile is just the median. 50th percentile and the median are the same thing. Because it has to be bigger than 50th percentile, it has to be bigger than half the data. If we just took the 7th number, that'd be the 30. It's only bigger than 6 of them and smaller than 7 of them. I want you guys to find 25th percentile for me. You're right, you get 3.5, so that means it's the 4th position. So it's the other 26. Now, in a small data set like this, we only have 14 numbers. We don't generally use percentiles unless we have like hundreds of numbers. One of the things you guys probably saw percentiles on the most, for those of you that remembered them or took them, like when you did the state testing or standardized testing, they might come back and say, you scored in the 78th percentile. That's what that is. There's thousands of people who took that test, and they're referring back. Here, the 70th percentile was that 40, right? But what if I asked you to find the 67th percentile? 9.38, which rounds up to the 10th position, which is still the 40, right? So it's the 67th percentile, it's also the 70th percentile. Well, guess what? It's like the 64th percentile to the 71st or 72nd percentile. Why? Well, because there's only 14 numbers in this list. Yeah. If you have 100 numbers, then each number is a single percentile, right? What if I go the other way? I want to know what percentile a number is. I'm going to give you a list of numbers again. I am going to put them in order as I write them. 1, 2. So there's my set of numbers. In this case, n equals 12. If I ask you what percentile is the 39? To find that percentile, there's a formula. It is the number that is smaller plus 1/2 of the number that are equal divided by n. That is the total number. Okay, so what does that mean? Well, percentile 39. Here's 39. How many numbers in this list are smaller than 39? 2 plus 1/2. How many are equal to 39? 1 over n is 12. So 2 plus 1/2 times 1. Well, what's 1/2 times 1? 1/2. 2 plus 1/2. 2.5 over 12, which gives us 0.208. We're going to round to 0.21. That is the 21st percentile. What percentile is the 58? How many numbers in this list are smaller than the 58? 9 plus 1/2 times how many are equal to 58? 1 divided by 12. So 9 plus 1/2 times 1? 9.5. 9.5 divided by 12. 0.79, so that's the 79th percentile. How about what percentile is the 44? In this list, how many numbers are smaller than 44? 4 plus 1/2 times how many are equal to 44? 2 divided by 12. 4 times 1/2 times 2, or 4 plus 1/2 times 2. 1/2 times 2 is 1. 4 plus 1 is 5. So that's 5/12, which is going to give us 0.416 to 0.42. That is the 42nd percentile. Not so bad. Better than a sharp stick in the eye. Okay, so let's talk about quartiles. Quartiles divide the data into 4 equal sections. Now let's think about this. If I have a board or a piece of metal or whatever, and I want to cut it into 4 pieces, how many cuts do I have? 3 cuts, right? So this is it's a big confusion. I get the question all the time. If it's quartiles, why aren't there 4 of them? Because the quartiles are the cuts. They're the cutoffs. It only takes 3 cutoffs to cut into 4 pieces. So there's quartile 1, quartile 2, and quartile 3. Cuts the data into the 4 equal pieces. Quartile 1 is simply 25th percentile. Quartile 2, anybody want to guess? 50th percentile. Anybody remember the other name for the 50th percentile? The median. And quartile 3, 75th percentile. So we know how to calculate them already. The question is, why are they important? Well, they're important because by dividing the data into 4 equal parts and then looking at their arrangement, we can say some pretty interesting things about the data. First of all, that bell curve we had, right? Where do we expect the data to be most concentrated? In the middle, right? And more spread out. So we would expect the quartiles, well, actually, let me step back up to that. The quartiles are used to make a plot called a box plot. sometimes called a box and whisker plot. What the box plot does is it takes the smallest number, the minimum, at the end of a whisker. Then it takes that first quarter to the median or the second quarter, up to the third quarter, and then up to the largest number, the maximum. This box plot shows 4 equal pieces. So these pieces, each of these sections of the box plot shows an equal number of data points. Each of that is 1/4 of the data. Well, for a normal curve, we'd expect the inside 1/4 of the data to be much tighter together, wouldn't we? So here's quartile 1, median, or quartile 2, and quartile 3. And the minimum and the maximum would be more spread out. So we would expect the middle of that box plot to be smaller than the whiskers. It's sometimes called a box and whisker plot. So those whiskers would be longer because the data is more spread out on the ends. So the smaller the section of the box plot, if this section is smaller, the closer the data points are, the more concentrated the pen is upsetting me today. The closer or more concentrated the data points are at that section. Larger means more spread out. From this, we come up with something called the interquartile range. Which from now on you'll hear me refer to as the IQR. I might say interquartile range, but I'm going to write IQR because I'm inherently lazy. The interquartile range is just the third quartile minus the first quartile. So let's look at a small set of data. There's my set of data. N equals 6, right? The min, smallest number, 7. Quartile 1, well, 6 times 0.25 is 1.5, rounds up to the second number, that'll be the 13th. The median, or quartile 2, 6 times 0.5 is 3, since that's a whole number, that means between the third and the fourth, right? Between 15 and 16, that's 15.5. Quartile 3, 6 times 0.75 is 4.5, rounds up to the fifth, 21. The max, 29. So there's 2 numbers I'm going to compare here. The range is 29 minus 7, or 22. The interquartile range is 21 minus 13, or 8. What does that tell us? What do those 2 numbers together tell us? Well, let's look at this box plot again. If I have a box plot like this where all the data is equally spread out, they call it uniformly distributed. If all the data is equally spread out, remember the range goes from there to there. The interquartile range, the IQR, goes from there to there. If the data was perfectly evenly spread out, how would we expect those 2 things to relate to each other? All the sections would be the same size, so the IQR is 2 of them, the range is 4 of them, so the IQR, the interquartile range, would be exactly half of the range, right? If it's less than half of the range, that means it's shaped like this, so these in the middle are smaller than the wings or the whiskers, which means it's more concentrated in the middle. right? More spread out on the ends, kind of like a normal distribution. If we have a range, let's say we have a range of 30 and an IQR of 20, what's that telling us? Yeah, that's telling us the data is actually spread out in the middle and concentrated on the ends. Kind of a weird looking distribution. So when we're looking in manufacturing, you shouldn't ever have uniformly distributed data. You should always have normally distributed data. The point should always be more concentrated towards the middle of the distribution. So a very quick check is always the interquartile range and the range. That interquartile range should always be less than half of the range. If that interquartile range is more than half of the range, you got some weird stuff going on. Usually what that is a temperature issue, where you have something that's expanding as it heats up. So at the beginning of the shift, you're getting a bunch of small numbers. As it heats up, you're getting a bunch of large numbers, and it very quickly goes from one to the other. Does that make sense? So it's in quality control, there's a lot of things. Now, that's all the new topics for the day, by the way. I'll give you homework in a second. This is kind of subtle. I admit that, getting that feeling for that interquartile range being smaller than half of the total range. When it comes to quality control and manufacturing, there are a lot of very subtle things. The first step is understanding the statistics that we're talking about now and the numbers behind them. But a bigger step to being good at quality control, and some of you may at some point be asked to be moved up into QR, quality assurance, 2A quality assurance and stuff. It's actually a great job. Less work, better pay. I shouldn't say less work, but less physically demanding work in most cases, better pay. And all it really is it's being very familiar with the process and having that feel for the process. Working with it over and over again and seeing what the data looks like and paying attention to those details so that when you look at it and something's different, you maybe don't know exactly what's different, but you know something's off. So, homework is going to be in your book. Page 692, exercise 32-5, problems 5 through 8.